knows about this?
Add your x's and add your y's.
That's exactly right. I like how she said this. So she's got prior knowledge of this. Anybody else know about vectors? Look at the hands in this room. Not every hand went up, but a lot of you are like, I got this stuff down. But I said, how do you add vectors together? Like, do you just add the magnitudes? She's like, no, 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 no. It's not that simple. You got to add the x's together and add the y's together. So what I'm saying is that when I drew a picture of this vector A, let me get this. Can we erase that B? Let's make another B. How about vector B be, I'm going to put it way down here. How about vector B goes 5 notches this way and 3 up. All right? And here's vector B. It goes like this. And you and I are going to add vector A plus vector B. Let me get this magnitude out of the way. Well, we'll do it two ways, algebraically and geometrically. Can I slide vectors? And I want you to slide this vector. So that right there is right at that tip. I mean, that's the tail of vector A, but I want you to put it there so this is the tip of it. I'm going to slide it here and put it right there. I'm just going to slide it. Just so you can see the geometry of this. So here comes vector B. I'm going to move it over here. It went how far? How far would it go then?
5 and 3.
And it had a length of 5, so now it's going to get out to what? 2, 3, 4, 5, 6. And how far up will it get? 3. So when I'm now going to slide this dude, and like this, and go up 1. Well, here it is. Here's vector B. And then I'm going to come back to what she said about how to do this algebraically.
Yeah. 3 from the 2.
Oh, you're the best, Owen. It's like I'm not going up 1 notch. I'm going up how high?
Going up to 3.
All right, so let me get this 2. If I go up 3, then 4, then what?
5.
Yeah, that's pretty much. All right. Start here. 5 this way. 3 this way. Vector B. I'll go like that on there. And when there's something called the triangle law for vectors. And this vector here plus this vector here will always equal the vector that starts here and stops there. That's called the triangle law. I'm going to put it with the white chalk. So this is first geometrically understanding how to add vectors together. Doom. Straight line distance, everyone. I'm going to call that vector C. In this representation, vector A plus vector B will equal vector C. Cool. Is that true? Geometrically, absolutely. And we're going to go back and do this algebraically, like she said. Do you remember? I go, how do you add these? She goes, you got to add the x's together, and then you got to add the y's together. That's going to be pretty easy. But I didn't want you to think you just added the magnitudes. Hey, so over here, what if I did this? There's vector A. There's vector B. What would be vector A plus B? Start here, and where would I stop?
B.
All right, so I'm going to start here and go like this. And right here, I can label this as a vector A plus vector B. Is that true? I think there's a problem on the problem set like this. You got to figure out like which one of the choices is true. Just apply this law. It's like, okay, I go here, and then I go to there. It's like a ship move. The ship moved from here to here, took a rest, stopped, then the ship moved from here to here. Where did it start originally and where did it stop? From there to there. Cool? All right. So now, come on back. We see vector C in there. Vector C is equal to what? A plus B. But how do we do this? And you said you add the what? The x's and you add the y's. So what was vector B's components? 5 and 3. This is all we're going to do. We're going to keep this simple. This is how you add vectors. Think, think. Even if you get positive and eggs in there, and I got both all positives here. What is vector A plus vector B? It's equal to, we can see it, this should be a 6, and how far is this?
5.
Is that what we see? That's why I wanted to do that one. I know, don't worry, I'm going to be using plenty of negative values in this course, but when you can see the math, when you can visualize it, it makes sense to you. She was exactly right by, hey, you just add the x's, add the y's. What if it's three-dimensional? Then you'll just add the what?
Z.
You
So,
got it.
and vectors we use this angular brackets.
That's right. Now, can we find that magnitude?
Yes.
How long is that? You're like, oh, I need the law of sines or something. Oh, nonsense. One theorem, the what? So what's the magnitude of a plus b? Okay, just do the square root of the what?
6
Square root plus 5 squared. What is that? 36.5, 60? Is that right? Is that the length? But I point this out when you're doing things, most of the time you can be doing things algebraically. And you'll go, ah, man, I don't know if my answer's right. I recommend just either make a mental picture or just draw a simple picture just to see if it comes out like realistically. You go, that can't be it. Because if I add these vectors, it should be like this. It should be like a 6 and a 5. Hey, this is called component notation. When I write it like this, that's your x component, that's your y component, x component, y component. This is called component notation. There's another Papa notation. I mean, the students in this class might have a physics professor who only uses this notation. It's standard basis notation. So let me show you what this is in standard basis notation. This right here will be written like this. Can everyone see way over here? All right, here it is. I use i's and j's. Ever heard of this? Okay, so I'm going to put 1 for emphasis. I'll put a little vector on top of that thing. Plus, this is called the I component, and this is called the J component. And I put a plus between these, and then I put 2J, and I'll put that arrow over there. Just to, the book, these will just be in boldface print. So the book will go, the textbook, your author, you know, he passed away a couple years ago, James Stewart, but he will go back and forth between these notations to get used to it. So I don't want you to think like, why does he keep switching? You're going to notice me, most of my presentations, I use this notation. I find it easier. You probably can tell it's less writing to just put a and to put all the little i's and the j's. And guess what letter we'll use for the z component?
Okay.
K. So it'll be I, j, and k components as like your x, y, and z components.
So this I has nothing to do with square root of -1.
That's right.
This I is square root of -1.
I mean, for
Like imaginary number. This I for vector.
oh gosh, I was like, what are you saying? I was like, you're right. This has nothing to do with that I, which is what?
Square root of -1.
Has nothing to do with that.
Okay.
You're right. I'm glad you brought that up. Someone else in this class might have been thinking like, is that the square root of -1? Nope. Everything in the real number system. It's just the letter they use.
Got it.
I know sometimes there's duplicate letters that we mean important have important meaning in mathematics,
Yeah.
and we see it again. Just the x component. So what would that be? 5i plus. Notice we put a plus between these. These you don't though, right? We just put commas in these funny looking braces that are new. Notice this isn't this brace that we use for set notation. Notice it isn't like the coordinates we use for x, y's, and z's. They're just a and that would be a 6i plus 5j, right? All right, cool. Hey, a couple more things with these vectors. The first thing is, here's vector A. Vector B. B went from here to here. And you know what vector negative B would be? I'll put it right on his picture. He nailed it. What was it?
It goes in the opposite direction.
It just goes in the opposite direction. Has the same magnitude. So if you want in this picture, I can just add to this picture, go, what would vector negative B look like? You go, oh, that would be a vector that just went in the complete opposite direction. I gotta make sure when I'm drawing this, I keep the same what? Same magnitude and just go, and you can just call that negative B. Is that far enough? Get a little bit farther, right? Close enough, right on? Alright. Hey, erase this. So So negative b is just a vector, goes in the complete opposite direction of vector b, same magnitude. So what would negative a here be? What would happen to these? These just be negatives? Do y'all agree? If it went what before? 1, 2? 1, 2? What would this be?
Negative 1, 2.
Yeah? Someone agree? I just multiply a negative 1 to both of those? Distributed?
Yeah.
Exactly. But would this have the same magnitude? Let me see. What's this magnitude?
0.
Negative 1 squared?
Plus,
What?
plus.
How long is that?
Five.
Does everyone agree? Has the same length, but what did that vector do? It just went in the opposite direction, but has the same magnitude. Cool? All right, very, very important word is next. You ready? Unit vector. All right. A unit vector. Definition of unit vector? A vector with a magnitude of 1. Like, has anyone ever seen the unit circle before? That's the circle with the radius of what? 1, center of the origin. She's like, trig. Hey, I put a trig sheet in Canvas in case everyone needs a brush up on trig. When the trig comes up today, I always just put like the special right triangles up and stuff like that, just so you get aware of that. You know, just so you know the cosine is 0 degrees, sine is 0 and all that. But a unit vector's definition, it's a vector
With
with the
magnitude.
length or magnitude of what?
1.
1. All because of this word what? Unit. All right, there's vector A. Well, if you want to, we can title it the vector U then. Can you help me find, right now, vector U, which is a unit vector in the same direction as vector A? So I'll write that on the board so you know what we're finding. Let's find a unit vector. But it's going to be in the same direction as which vector? Of A. See, everyone, I know that's not a unit vector. That doesn't have a length of 1. What's this? When I say length, I'm talking about the magnitude. What was the length of that? What's cool is a lot of you do it mentally. Can you do it in your head? What's the square of that square plus that square? We had it written before. What
Root
is
5.
it?
Square.
Square root of 5. That's its length, right, everyone? Well, then that's not a length of 1. Square root of 5 is a little bit over 2. Right? We just got to shrink it down a little bit. Well, the cool thing about vectors is that when you can multiply any scalar value to it, they call it a scalar multiple to it. So that's all we're going to do. For vector U, everyone, I'm getting ready. I'm going to keep these here. This is going to have the same direction as A. I just got to multiply a number here. And that's what I'm here to. Dealt with that magnitude, but you don't put it in front. You have to what? Divide by it. So that's the formula. We're going to take 1, we're going to divide by that magnitude. And that's how we'll find a unit vector every time. What do? To find this unit vector in this direction, it's going to have a length of 1. I just divide out this magnitude. What was the magnitude?
Square root of 5.
Now, can I leave my answer like that? Sure. Sure you can. What's some other ways to write it? You could distribute it. What would that look like?
1 over square root
1
of
over
5.
5, 2 over root 5. Does anyone here like to rationalize denominators? He can. He's like, you don't have to. All right, leave it like that. That looks pretty neat, right? Could you put the i's into j's?
Yep.
Sure. You could do 1 over square root of 5 I plus 2 over the square root of 5 j. But everyone, that is a unit vector. Its length is how long? Like if I drew it and I measured the length with the measuring tape, it's got a length of 1. But it still has the same direction as what? This. It's a scalar multiple of this. That's what's cool. So let's put down a little formula. It's on the formula sheet. But what's the formula for any unit vector in the direction of any vector A? It's you take vector A, but you always divide out the what?
Magnitude.
Will that work? And then there's the formula for unit vector. We say any unit vector in the direction of the vector A, you have vector A, but you in front you're going to divide out. I'll put a parentheses around this if it helps. Divide out the what? Magnitude. I know. We don't multiply it in the numerator. That can make it longer, right? Good deal. All right. So that leads us to a question. I believe you'll see one of these on the problem set. You'll see them in the textbook as well. And when I'm going to make up a vector, this time though I'm making it three-dimensional. Can you find a length? No. Not find the length. I need you to find a vector. That is in the same direction as, all right, here comes a three-dimensional vector. Vector v, -2, 3, 4. It's got to be in that same direction. And has a length of 8. And for length, I'm going to put parentheses magnitude. Alright. I'll let you write all that out. This is in 12.2. I mean, let's find a vector. It's in the same direction as vector -2, 3, 4. But it has a length of 8. Where do we start? Oh, let's start here. Is that what you're going to say?
I was going to find the magnitude of vector v.
That's a great starting point. Let's get that magnitude of vector v. And let's go here first. Now what will that length be?
1/8.
That one great? What we'll do is, let's find this magnitude. We'll divide it out. We'll write it like this. And that vector, we can put a u in front of it. But that vector is going to have a length of what? 1. So you and I know how to make a vector that's in the same direction that has a length of what?
1.
And then this part's going to be easy. We'll just multiply the numerator by what? 8. There you go. But that's where we start.